What if the next generation of humans isn't born on Earth? Imagine our descendants with entirely new senses, altered physiologies, and minds shaped by the vacuum of space. How will life beyond our home planet fundamentally change what it means to be human? The question isn't science fiction anymore. As we stand on the threshold of becoming an interplanetary species, we must confront a profound reality. Space won't just be a place we visit. It will be a crucible that reshapes everything about us. For millions of years, Earth has been our only home, our only laboratory for evolution. Every aspect of our biology, from the way we walk upright to the structure of our eyes, has been sculpted by this planet's specific conditions. But what happens when we leave? What happens when humans spend not days or months, but generations in environments fundamentally alien to everything our species has known? The answers will redefine humanity itself. The Cosmic Cradle, Earth's evolutionary legacy. To understand where we're going, we need to grasp where we've been. Human evolution on Earth has been driven by three fundamental forces: natural selection, environmental pressures, and increasingly, our own technological advancement. Over approximately 7 million years, our lineage diverged from other great apes, developing larger brains, complex language, and the ability to manipulate our environment in unprecedented ways. Natural selection operated through a simple but powerful mechanism. Individuals with traits better suited to their environment were more likely to survive and reproduce, passing those advantageous traits to their offspring. For our ancestors, this meant developing bipedalism to traverse African savannas more efficiently, growing larger brains to solve complex social and environmental challenges, and evolving sweat glands that allowed sustained physical exertion even in equatorial heat. Environmental pressures shaped us in countless ways. Ice ages selected for individuals who could innovate, create clothing and shelter, and work cooperatively. Dietary changes from primarily plant-based to omnivorous eating drove changes in our digestive systems and jaw structures. The transition from nomadic hunter-gatherers to agricultural societies roughly 10,000 years ago created entirely new selection pressures, including increased exposure to diseases from domesticated animals and higher population densities. But here's where human evolution diverges from almost every other species on Earth. About 50,000 years ago, something extraordinary happened. Our capacity for symbolic thought, abstract reasoning, and cumulative cultural knowledge reached a tipping point. We began to evolve not just biologically, but culturally and technologically. We created tools that extended our physical capabilities, clothing that allowed us to inhabit hostile climates, and eventually medicine that could overcome biological limitations. This technological evolution accelerated exponentially. Fire gave us cooked food, changing our nutritional intake and even our gut anatomy. Agriculture reshaped our societies and our genomes, with populations that adopted dairy farming developing lactose tolerance in adulthood. Written language allowed knowledge to persist across generations without biological encoding. In the last century alone, we've developed antibiotics that defeat bacterial infections, vaccines that prevent deadly diseases, and now genetic technologies that can read and potentially rewrite our own DNA. The Earth that shaped us had specific parameters: gravity pulling at precisely 9.8 meters per second squared, an atmosphere with 21% oxygen, a magnetic field shielding us from cosmic radiation, a day-night cycle of 24 hours, seasonal variations driven by our planet's axial tilt, temperature ranges that keep water liquid across much of the surface. Every cell in your body, every instinct, every automatic biological process evolved under these exact conditions. Consider something as simple as your cardiovascular system. Your heart pumps blood against Earth's gravity, working hardest when you stand up because blood must be pushed upward to your brain. Your muscles and bones grew dense and strong because they constantly resist gravitational pull. Your inner ear contains tiny crystals suspended in fluid, their position telling your brain which way is up. Your entire sense of balance, your proprioception, your very understanding of spatial relationships developed in Earth's gravitational field. Now imagine removing that foundation. Imagine multiple generations growing up without ever experiencing weight, without their bones bearing load, without their hearts having to fight gravity. This isn't speculation. This is the reality awaiting humanity as we venture beyond Earth. And the changes won't be superficial. They'll reach into the deepest levels of our biology, potentially creating humans so different from us that the term human itself may need redefinition. Gravity's grip and genetic drift. The transformation begins immediately. Within hours of entering microgravity, the human body starts adapting to its new environment. Fluids that normally pool in the legs due to gravity redistribute throughout the body, creating a puffy face and skinny legs that astronauts call bird legs. The spine elongates as the vertebrae separate without gravitational compression, making astronauts temporarily taller. The heart, no longer working against gravity, begins to atrophy like any underused muscle. But these are just the opening moves in a much longer game. Extended stays in space reveal deeper, more concerning changes. Bone density decreases at roughly 1 to 2% per month in microgravity. On Earth, your bones constantly remodel themselves, breaking down old tissue and building new material in response to mechanical stress. Walk, run, or simply stand, and your bones receive signals to stay strong. In space, those signals vanish. The body interprets the lack of load bearing as evidence that dense, heavy bones are unnecessary and metabolic expense that can be reduced. Astronauts on the International Space Station exercise for roughly 2 hours daily with specially designed resistance equipment, yet they still lose bone mass. Current countermeasures can slow, but not entirely prevent this loss. After 6 months in orbit, astronauts have bone density comparable to elderly individuals with osteoporosis. Some of this loss can be recovered upon returning to Earth, but not all. Studies suggest that certain bone sites may never fully regenerate. Muscle atrophy follows a similar pattern, though it manifests faster than bone loss. Without gravity to resist, muscles weaken and shrink. The anti-gravity muscles, those that keep you upright on Earth, degrade most rapidly. Calves, thighs, back, and neck muscles all diminish. The heart itself, that most crucial muscle, adapts to its easier workload by becoming smaller and less powerful. When astronauts return to Earth, many struggle to stand without assistance, their bodies temporarily unable to cope with the gravitational field they evolved to inhabit. The cardiovascular system undergoes other profound changes. On Earth, your heart and blood vessels maintain blood pressure carefully calibrated for vertical living. Stand up quickly, and vessels in your legs constrict while your heart rate increases, preventing blood from pooling away from your brain. In microgravity, these reflexes deteriorate. The volume of blood plasma itself decreases, as the body decides it's carrying more fluid than necessary. When astronauts return to Earth, many experience orthostatic intolerance, difficulty maintaining blood pressure when standing, causing dizziness or fainting. Consider what this means for a child born in space. They would develop without ever experiencing the mechanical stresses that shape human skeletal and muscular systems. Their bones might grow longer and more slender, optimized for a microgravity environment rather than Earth's pull. Their cardiovascular system would develop entirely differently, never learning to fight gravity. Their proprioceptive systems, their internal sense of body position and movement, would wire themselves according to a three-dimensional environment without an inherent up or down. Such a child might be perfectly adapted for life in a space station or spacecraft, but potentially unable to ever visit Earth. Their bone structure might not support their own body weight in full gravity. Their heart might lack the power to pump blood against gravitational pull. They would be, in a very real sense, a different kind of human, one native to space rather than Earth. Mars presents a different but equally challenging scenario. Martian gravity is approximately 38% of Earth's, strong enough to provide some structure and orientation, but weak enough to cause significant long-term changes. We don't yet know the full implications of partial gravity on human development. Would Martian-born humans develop bones and muscles intermediate between Earth and microgravity adaptations? Would 38% be sufficient to maintain cardiovascular health? These questions remain unanswered. Radiation exposure adds another layer of complexity. Earth's atmosphere and magnetic field shield us from cosmic radiation and solar particle events. Space offers no such protection. The International Space Station orbits within Earth's magnetosphere, receiving some protection, but astronauts still accumulate radiation exposure far exceeding what they'd encounter on Earth. Mars lacks a global magnetic field and has only a thin atmosphere, offering minimal shielding. This radiation doesn't just pose immediate health risks, it damages DNA, causing mutations that could be passed to offspring. Over generations, populations living in high radiation environments would accumulate genetic changes at accelerated rates. Some mutations would be harmful, potentially increasing cancer rates and birth defects. But others might be neutral or even beneficial, potentially activating dormant DNA repair mechanisms or creating novel radiation-resistant traits. The isolation of space populations would amplify these effects through genetic drift. On Earth, human populations intermix, spreading genetic variations widely. A mutation that arises in one individual can eventually disseminate across entire continents. But space colonies, especially in the early stages, would likely be small and relatively isolated from Earth and each other. Small populations are subject to genetic drift, random changes in gene frequencies that can occur regardless of whether traits are beneficial or harmful. Imagine a Mars colony of a few hundred or thousand individuals. Any genetic traits present in the founding population would be overrepresented in subsequent generations compared to Earth's population. Rare traits could become common through random chance. Beneficial adaptations could spread rapidly through the limited gene pool. Over many generations, Martian humans could diverge significantly from Earth humans simply through the mathematics of small population genetics. This process would accelerate if different colonies remain genetically isolated from one another. A colony on Mars might develop differently from one on the moons of Jupiter or in orbital habitats near Earth. Each environment would present unique selection pressures. Each small population would undergo its own genetic drift. Given enough time, given enough isolation, we could see the emergence of distinct human subspecies, or even separate species, each adapted to their particular cosmic niche. The question is how long this would take. Evolution typically operates on timescales of thousands or millions of years. But humans in space would face selection pressures more intense than almost anything our species encountered on Earth. The environment would be immediately hostile, with survival depending on specific adaptations. Genetic drift would operate more powerfully in small populations. And unlike natural evolution, we possess the technology to potentially accelerate these changes deliberately. New forms, new minds, adaptive pathways. Let's envision humanity 1,000 years from now, with substantial populations living beyond Earth for dozens of generations. What might these space-adapted humans look like? What capabilities might they develop? The possibilities range from subtle modifications to transformations that would make them barely recognizable as human by our current standards. Physical adaptations would likely appear first. Reduced gravity would favor tall, slender body types with elongated limbs. Dense, heavy bone structure would be disadvantageous in microgravity, so bones might become lighter and more porous while developing different internal architectures to handle the mechanical stresses unique to space habitats. Muscle distribution would shift, with reduced emphasis on anti-gravity muscles, and potentially enhanced finger and hand strength for maneuvering in three-dimensional environments. The skull might undergo interesting changes. In microgravity, the spine lengthens and the brain experiences slight shifts within the cranium. Long-term adaptation might involve skull modifications that accommodate these changes more comfortably. Eye sockets might evolve to better protect against radiation exposure. The sinuses, which cause problems in microgravity as fluids don't drain properly, might reduce in size or alter their structure entirely. Radiation resistance could develop through multiple pathways. Some organisms on Earth already possess remarkable radiation tolerance. The bacterium Deinococcus radiodurans can survive radiation doses thousands of times higher than would kill a human, thanks to redundant copies of its genome and highly efficient DNA repair mechanisms. Tardigrades, microscopic animals that can survive the vacuum of space, produce proteins that protect their DNA from radiation damage. While humans wouldn't spontaneously develop these exact mechanisms, selection pressure in high radiation environments might favor individuals with more robust DNA repair systems. Skin might evolve increased melanin production for radiation protection, or perhaps entirely novel protective compounds. Internal organs could develop redundancies, with multiple smaller versions of critical systems, rather than single large organs. reducing the impact if one is damaged by radiation. Cellular mechanisms for detecting and repairing radiation damage might become more efficient, selected for across generations of space inhabitants. The cardiovascular system in permanent microgravity environments might transform dramatically. With no need to pump blood against gravity, heart structure could change substantially. Blood vessels might remodel themselves, potentially becoming more uniform in size and structure without the need for the pressure gradients required on Earth. The entire circulatory system might optimize itself for three-dimensional flow rather than the vertical orientation Earth's gravity demands. Sensory systems could evolve in fascinating directions. The vestibular system, which governs balance on Earth, would need complete rewiring for microgravity environments. Space-adapted humans might develop enhanced proprioception, a more acute sense of their body's position and movement in three-dimensional space. Vision might shift to emphasize peripheral awareness, better suited for environments where threats and opportunities can come from any direction, not just ground level. Some researchers speculate about more exotic adaptations. Could humans develop magnetoreception, the ability to sense magnetic fields, to help navigate in space? Some animals on Earth possess this sense, using it for migration. Birds, sea turtles, and even some bacteria can detect Earth's magnetic field. The biological mechanisms are still being researched, but they involve specialized cells containing magnetic crystals or proteins sensitive to magnetic fields. Space-dwelling humans might benefit from such a sense to orient themselves relative to planetary magnetic fields or artificial fields in spacecraft. What about the human brain? Our brains are our most distinctively human feature, the organ that makes us intelligent, creative, and self-aware. How might cognition change in space environments? The brain is remarkably plastic, especially during development. Children raised in microgravity might develop spatial reasoning capabilities surpassing Earth-bound humans, their brains wiring themselves for true three-dimensional thinking rather than the modified two-dimensional thinking we practice on Earth's surface. Language might evolve new components. Hand gestures and body orientation carry meaning in microgravity that they can't on Earth. A complex sign language optimized for three-dimensional space might develop, eventually influencing spoken language or even replacing it in some contexts. The brain regions associated with spatial processing and motor control might enlarge relative to other areas. Social structures could shift in ways that feed back into evolutionary pressures. Space habitats would likely require high degrees of cooperation and interdependence for survival. Individuals with strong prosocial traits, empathy, communication skills, and ability to work in teams might have reproductive advantages. Aggressive antisocial tendencies could be selected against in close-quarters environments where conflict poses existential risks to entire communities. Reproductive biology itself might change. Human pregnancy and childbirth evolved under Earth's gravity. We don't yet know if human reproduction is even possible in microgravity. Animal studies suggest potential problems. Pregnant rats flown in space showed abnormalities in fetal development. The orientation of the fetus, the development of the vestibular system, even the process of labor and delivery might not work properly without gravity. If natural reproduction proves difficult or impossible in microgravity, space populations might require artificial wombs or other reproductive technologies. This would remove natural childbirth as a selection pressure entirely, potentially allowing other traits to be emphasized instead. Or perhaps humans would adapt, with the reproductive system evolving to function in microgravity, developing new mechanisms to protect and orient the fetus without relying on gravity. Longevity could be affected in either direction. The harsh space environment, with its radiation, isolation, and psychological stresses, might reduce lifespans. Or the careful control of habitat conditions, combined with advanced medical technology and selection for radiation resistance and other survival traits, might extend lifespans beyond Earth norms. Some researchers speculate that reduced gravity might actually slow certain aging processes, as the cardiovascular system experiences less cumulative stress over a lifetime. Consider the more distant future, with humans adapting to radically different environments. Colonies in the clouds of Venus would face crushing atmospheric pressure and extreme heat, requiring completely different adaptations than microgravity habitats. Settlements on the icy moons of Jupiter and Saturn would need to cope with extreme cold and high radiation from their host planets. Each environment would drive evolution in different directions. Given sufficient time and isolation, we could see the emergence of distinct human species. A formal biological species is typically defined as a group that can interbreed and produce fertile offspring. If Martian humans and Earth humans became different enough genetically, they might no longer be able to produce viable offspring together. At that point, they would be separate species, both descended from modern Homo sapiens but diverged into new forms. This speciation could happen faster than traditional evolution suggests if enhanced by intentional genetic modification. But even without intervention, the combination of isolation, genetic drift, and intense selection pressures could accomplish it within 10 to 20,000 years, a blink of an eye in evolutionary time. We could witness the birth of Homo spatialis, Homo martialis, or even more exotic variants adapted to environments we haven't yet imagined. The ethical quandaries of directed evolution. Here's where the story becomes uncomfortable. We don't have to wait for natural selection. We could actively reshape human genetics for space adaptation right now, or at least within the next few decades. The technology already exists in primitive form. CRISPR gene editing allows precise modifications to DNA sequences. We can already alter the genes of human embryos, though ethical concerns and regulations restrict such experiments in most countries. The question isn't whether we can modify human genetics for space. The question is whether we should, and if so, how and who decides. These are some of the most profound ethical dilemmas humanity has ever faced. The answers will shape not just our future in space, but what it means to be human at all. Consider the practical arguments for genetic modification. Natural adaptation takes thousands of generations. We can't wait that long if we want to establish space colonies within the next few centuries. Astronauts currently face serious health risks from radiation, bone loss, and cardiovascular problems. These risks worsen with longer missions. A journey to Mars takes months. A trip to the outer solar system could take years or decades with current propulsion technology. Without biological modifications, such missions might be impossible for unmodified humans to survive. What if we could edit human embryos to produce individuals with enhanced radiation resistance? Dense, radiation-tolerant cells, improved DNA repair mechanisms, perhaps even borrowed genes from radiation-resistant organisms? Such individuals could survive and thrive in environments that would kill unmodified humans. They could explore and settle worlds that would otherwise remain forever beyond our reach. Or consider modifications for reduced gravity. What if we could program embryonic development to produce lighter bone structures and different muscle distributions from birth? Such individuals would be pre-adapted to space environments, suffering none of the debilitating effects current astronauts endure. They could live full, healthy lives in space habitats or on low-gravity worlds without the constant medical interventions required to keep unmodified humans functional. These modifications could be framed as medical interventions, preventing disease rather than creating enhancement. Osteoporosis in space is a medical condition. Cardiovascular deconditioning causes real health problems. If we can prevent these conditions through genetic modification, isn't that simply good medicine? We already use genetic screening to identify and sometimes prevent heritable diseases. Modifying genes to prevent space-induced illness seems like a logical extension. But the ethical problems multiply rapidly under examination. First, these modifications would be made to embryos, individuals who cannot consent to alterations that will affect their entire lives. We'd be making decisions about what kind of body and perhaps mind they'll have without their input. True, parents already make countless decisions affecting their children's lives, but genetic modifications are fundamentally different. They're permanent, heritable, and could affect the individual in ways we can't fully predict. Second, optimizing humans for space might make them maladapted to Earth. A person genetically engineered for microgravity might have bones too weak to support their body weight in Earth's gravity. They might be unable to visit the planet of their species' origin, effectively exiled to space for their entire lives. Are we justified in creating humans who can never experience Earth? Would such individuals even be considered fully human by Earth's population? Third, Who decides what modifications are acceptable? Enhanced radiation resistance might seem like an obvious choice, but what about modifications for appearance, intelligence, or personality traits? If we're editing genes anyway, why not optimize for other characteristics? But optimization according to whose values? Different cultures, societies, and individuals have radically different ideas about what traits are desirable. Engineering humans to fit specific templates starts to resemble eugenics, the discredited pseudoscience that caused immense suffering in the 20th century. Fourth, genetic modifications could create new forms of inequality. Initially, such technologies would be expensive and available only to wealthy individuals or well-funded space programs. We could see the emergence of a genetic divide, with modified humans possessing capabilities unmodified humans lack. Over time, this could create separate classes or castes, with profound implications for social justice and human rights. The gap between enhanced and unenhanced humans could make current economic inequalities look trivial by comparison. Fifth, unintended consequences are almost guaranteed. Genes don't work in isolation. They interact with each other and with environmental factors in enormously complex ways we don't fully understand. Modifying one gene to achieve a desired trait could have unexpected effects on other traits. We might solve the radiation resistance problem only to create new health issues we didn't anticipate. The history of technology is filled with unforeseen consequences. The stakes are much higher when we're experimenting on human biology. Religious and philosophical objections add another dimension. Many belief systems hold that humans are sacred, created in a divine image or possessing inherent dignity that shouldn't be tampered with. Deliberately altering human nature could be seen as hubris, playing God, or violating the fundamental essence of what makes us human. Even secular philosophies grapple with the question of whether we have the wisdom to redesign ourselves, whether we should cross certain lines even if we technically can. Some ethicists argue for a precautionary approach. Given the profound uncertainties and potential for catastrophic mistakes, we should proceed extremely slowly, if at all, with heritable genetic modifications. Others counter that the precautionary principle cuts both ways. Failing to adapt humans for space could strand our species on a single planet, vulnerable to extinction from asteroid impacts, climate catastrophes, or other existential risks. Perhaps the greater danger lies in remaining purely Earth-adapted. There's also the question of reversibility. Once modified humans reproduce, their engineered traits pass to subsequent generations. If we make mistakes or decide certain modifications were unwise, we can't simply undo them. They become permanent features of the human genome, for better or worse. We'd be editing not just individuals, but the entire future human lineage descending from them. Consent becomes especially fraught across generations. Even if the first generation of modified humans consents as adults to modify their own embryos, those embryos grow into people who might have different values and preferences. And their children, and their children's children, inheriting traits chosen by distant ancestors according to values and knowledge that may become obsolete. How many generations forward do we have the right to make choices? International cooperation and regulation present practical challenges. No single nation controls space or has authority over human genetic modification globally. What happens if some countries ban certain modifications while others permit or encourage them? We could see genetic tourism, with people traveling to permissive jurisdictions to access forbidden technologies. Or genetic divergence driven by policy differences rather than environment, with some nations producing modified populations while others maintain genetic conservation. The military implications are impossible to ignore. Genetically enhanced humans with improved strength, endurance, cognitive abilities, or other traits would have obvious advantages in conflict. An arms race in human genetic engineering could emerge, with nations competing to produce superior populations for strategic advantage. This could accelerate genetic modification in reckless and dangerous ways, with national security concerns overriding ethical caution. Perhaps most fundamentally, these questions force us to confront what we value about being human. Is there some essential quality that must be preserved, some line that shouldn't be crossed? Or is humanity defined not by specific biological traits, but by consciousness, self-awareness, creativity, and culture? Can we modify the biological substrate extensively while preserving what truly matters? And who makes that determination? Different ethical frameworks reach different conclusions. Utilitarian ethics might favor genetic modification if it maximizes overall well-being and allows more humans to live flourishing lives in space. Deontological ethics might emphasize inviolable rules about human dignity and consent, prohibiting modifications regardless of potential benefits. Virtue ethics might ask what genetic engineering does to human character and relationships, whether it cultivates virtues or vices. No framework provides easy answers. We may need entirely new ethical principles for this unprecedented situation. Traditional human rights frameworks assume a relatively stable definition of human nature. Genetic engineering challenges that assumption. Do enhanced humans have the same rights as unmodified humans? Do we have obligations to potential future people who might be harmed by our genetic choices? How do we balance individual liberty to modify oneself or one's offspring against collective concerns about human nature and social cohesion? One thing seems certain: these decisions can't be left to scientists and engineers alone. The implications are too profound, affecting philosophy, religion, politics, law, and social justice. Any path forward requires extensive public deliberation, international cooperation, and perhaps most importantly, humility about the limits of our knowledge and foresight. We're contemplating changes that will echo through millions of years of future human history. That responsibility demands the most careful thought our species can muster. Beyond biology, technological transcendence. But there's another path, one that might sidestep biological modification entirely or supplement it so profoundly that the distinction becomes meaningless. Instead of slowly adapting human biology to space through genetics, we could rapidly enhance humans through technology. Cybernetic implants, artificial organs, brain-computer interfaces, nanotechnology, and ultimately perhaps uploading consciousness to non-biological substrates entirely. This technological approach offers certain advantages over genetic engineering. It's reversible in principle. It can be applied to existing adult humans who can consent. It doesn't create heritable changes that affect future generations. It could be faster and more flexible, allowing humans to adapt to different environments by swapping out modules rather than requiring separate genetic lineages for each niche. Consider the most straightforward interventions. Artificial organs could replace biological ones prone to problems in space. Hearts designed for microgravity could be implanted, optimized for the space environment without the limitations of organs that evolved for Earth. Artificial bones could be stronger and lighter than biological ones, resistant to the deterioration that plagues astronauts. Synthetic muscles could maintain strength without constant exercise. Artificial eyes could see wavelengths of light invisible to biological vision, detecting radiation or seeing in near total darkness. The cardiovascular system could be entirely reimagined. Instead of a single heart pumping blood through passive vessels, imagine a distributed circulatory system with multiple small pumps throughout the body. Or perhaps electromagnetic systems that move specially designed blood cells without mechanical pumping at all. In microgravity, without the constraints imposed by fighting gravity, radical redesigns become possible. Radiation protection could come from technological rather than biological adaptations. Implanted devices could detect radiation exposure and trigger protective responses. Nanomachines in the bloodstream could repair radiation damage to DNA and cells continuously. Artificial skin or external shields could block radiation while remaining flexible and comfortable. The body could become a hybrid system. With technology handling problems, biological evolution would take millennia to solve. Brain-computer interfaces represent a more profound integration of technology and biology. Early versions already exist, allowing paralyzed patients to control computer cursors or prosthetic limbs with their thoughts. Future versions could be far more sophisticated, creating direct communication channels between biological brains and computer systems. A space colonist with advanced neural interfaces could control their habitat systems directly, communicate with others through pure thought, access vast information databases instantly, or even share experiences and memories directly. Such interfaces could enhance cognitive abilities beyond biological limits. Working memory could be augmented with computer memory. processing speed could be accelerated. Multiple streams of information could be managed simultaneously. A human with advanced neural enhancement might think as far beyond current humans as we think beyond our distant ancestors. The implications for solving complex problems, managing spacecraft systems, or conducting scientific research are staggering. Navigation in space could become intuitive through technological augmentation. Implants providing constant awareness of orientation relative to magnetic fields, gravitational sources, or astronomical coordinates could create an innate sense of direction in three-dimensional space. Humans could develop what amounts to a technological sixth sense, perceiving aspects of their environment biological senses can't detect. Life support could be internalized. Instead of relying entirely on habitat atmospheres, humans could have technological augmentation of their respiratory systems. Perhaps artificial lungs, far more efficient than biological ones, or even systems that extract oxygen from alternative sources. Temperature regulation could be managed through technological means, allowing survival in extreme environments without bulky, protective suits. The ultimate extension of this technological path leads to a provocative destination: the possibility of uploading human consciousness to non-biological substrates entirely. If consciousness is an emergent property of information processing in the brain, and if we can map and replicate that processing in computer systems, then theoretically minds could exist without biological bodies at all. This concept, often called mind uploading or whole brain emulation, remains firmly in the realm of speculation. We don't yet understand consciousness well enough to know if it's possible. The philosophical questions alone are profound. Would an uploaded mind be the same person or a copy? Would it be conscious in the same way biological humans are? These questions touch on ancient puzzles about personal identity, the nature of self, and what consciousness actually is. But if possible, mind uploading would solve nearly every problem of biological adaptation to space. Digital minds wouldn't need oxygen, food, or protection from radiation. They could be backed up, copied, transmitted at light speed across interstellar distances. They could inhabit robotic bodies when physical interaction is needed and exist in virtual environments when it's not. They could survive indefinitely, limited only by the maintenance of their hardware substrates. Space exploration could be transformed. Instead of sending fragile biological humans on decades-long journeys to distant star systems, we could transmit uploaded minds as information, rebuilding them in robotic bodies upon arrival. The energy and resource requirements would be orders of magnitude lower than supporting biological humans for such voyages. We could explore the galaxy in ways that meat-based biology might never allow. Yet this path raises ethical and philosophical problems as thorny as those surrounding genetic engineering. Is an uploaded mind really the original person or a sophisticated copy? If the biological original continues to exist after uploading, which one is the real person? If we can copy digital minds, does each copy have the same rights and moral status as the original? Can we delete a mind? Would that be murder? The loss of biological embodiment could have profound psychological effects. Human experience is deeply rooted in having a body, in physical sensations, in biological drives and emotions. Would uploaded minds retain human psychology without biological hormones, without the felt experience of breathing, heartbeats, and physical touch? They might become something else entirely, posthuman intelligences with values and experiences radically alien to biological humans. The technology itself poses immense challenges. The human brain contains roughly 86 billion neurons, each forming thousands of connections to other neurons. Mapping this network at sufficient resolution to capture its information processing properties is beyond current technology. Then there's the question of replicating not just structure but function, understanding how the physical and chemical processes of neurons produce thought and experience. We're likely decades or centuries from having the capability to upload minds, if it's possible at all. Even simpler technological enhancements face obstacles. Implantable devices must be biocompatible, avoiding rejection by the immune system. They need power sources that can last years or decades without replacement. Neural interfaces must connect to biological tissue without causing damage or inflammation. These are solvable engineering problems, but solutions will take time to develop and refine. There's also the question of equity and access. Early technological enhancements will be expensive, available only to wealthy individuals or well-funded organizations. This could create divisions between enhanced and unenhanced humans similar to those posed by genetic engineering, but potentially reversible since technology can theoretically be removed or made accessible to more people as costs decrease. Humans might follow multiple paths simultaneously. Some populations might pursue biological adaptation through genetic engineering. Others might choose technological enhancement. Still others might remain relatively unmodified, preserving baseline human biology as a kind of conservation effort. Over time, these groups could diverge into distinct varieties of human or post-human existence, each with advantages and disadvantages for different environments and purposes. The interaction between biological evolution and technological enhancement could create feedback loops. Genetic modifications might make individuals more compatible with technological implants. Technological enhancements might create new selection pressures, favoring individuals whose biology integrates best with technology. The boundary between biological and technological could blur until the distinction becomes meaningless. We might reach a point where human becomes more of a philosophical category than a biological one. If you have an enhanced brain, artificial organs, nanomachines in your bloodstream, and cybernetic limbs, are you still human? What if only your brain is biological, housed in an entirely artificial body? What if your biological brain is heavily modified to interface with computers? At what point do we transition from human to post-human? Perhaps the answer is that it doesn't matter. Perhaps what makes us human isn't specific biological features, but consciousness, self-awareness, the ability to think, feel, create, and relate to others. Perhaps humanity is defined by continuity of culture and identity rather than continuity of biology. If we modify ourselves extensively but retain our values, memories, and sense of being human, perhaps we remain human in the only ways that truly matter. Or perhaps we should embrace the transition to something beyond human. Our ancestors weren't Homo sapiens. We evolved from earlier hominins, who evolved from earlier primates, who evolved from earlier mammals, stretching back millions of years. Speciation is natural. Change is inevitable. Perhaps attempting to preserve a static definition of humanity is futile and even undesirable. Perhaps we should accept that space will transform us, creating new forms of existence we can't yet imagine.